En breve, buenas tardes a todos. En breves comenzamos. En breve le damos la palabra a la doctora María para que haga la presentación del doctor profesor Kevin Dykema. A las 12 en punto comenzamos. Bien, buenas tardes a todos. Gracias a todos los que hoy están conectados por acá, siempre en este seminario de educación matemática que organizan los programas de maestría y doctorado en educación matemática de la Universidad Antonio Nariño. Queremos agradecer a todos los participantes que se encuentran hoy, también a profesor Luis Medina, adscrito al Magíster de Matemática, y al profesor Jonathan Rodríguez, director del Magíster de Matemática de la Universidad de Antofagasta en Chile, y que también está con nosotros, nos acompaña el vicerrector de investigación, el doctor Alfonso. Bienvenidos todos, doctora Mari.
Muchas gracias, Osvaldo. We are very happy to welcome you to our Wednesday afternoon seminar, Professor Dykema. We have high expectations of what you will be able to share with us as president of the NCTM and as a person whose trajectory in math education is very, very interesting for all of us. Without further ado, I give the meeting over to you.
Wonderful. Thank you very much. And I am delighted to be with you here this afternoon, and I hope that each of you are doing well. So I want to just begin by saying thanks. Thanks for all that you do to promote high-quality mathematics education in whatever role that you play. It's a wonderful subject, a subject that we all love, and it's one that not all the time do our students always share that same enthusiasm for. So I thank you for all that you do to try to make math an enjoyable subject and a worthwhile subject for all of your students. So as was shared, I am the current president of NCTM, and I want to just share our mission statement. The part that always resonates, that always hits me, is this last little bit, this each and every student. What am I doing to better meet the needs of every single one of my students? Not just those who think that they are good at math, but those who may think they're not good at math. What am I doing? Because every single student, every single human being deserves to have a good, high-quality mathematics education. And we try to continually push to help all mathematics educators really focus in on what are we doing to meet the needs of every single one of our students. But I want to begin our time together this afternoon thinking about what is mathematics. So I'm going to pause for a brief moment, and I want you to consider, how would you respond if somebody asked you, what is mathematics? I would guess that many of us on this Zoom call would say things like problem solving, reasoning, sense making, and those are all wonderful answers. I'm going to make the assumption that many of us would not say things like just finding the answer to a problem. Although if we think about many non-mathematics educators, when they hear math, many of them think it's just finding an answer to a problem. That is part of math, but math is so much more powerful, so much more beautiful than strictly answer getting. And I think the answer, the way that we view mathematics, affects the way that we see that mathematics should be taught. When we view it as a subject that applies to the real world, a subject that makes sense of what's going on, one that's about critical thinking, supporting our reasoning, mathematics should be taught differently than if we view it strictly as getting the correct answer to a problem. So for me, as an early career teacher, and I've taught grade 8 for over 25 years, in my initial teaching, I viewed it very much as just getting an answer to a problem. And my students were not nearly as excited as I was about math. And then right around 2000, in the United States, the National Research Council released a document called Adding It Up. And in that document, they talk about 5 different strands of mathematical proficiency. What does it mean to be good at math? What should mathematics education be focused on? And you see those 5 strands there. I had spent my early career really focusing in on that procedural fluency. But that's only one of those 5. There's this idea of conceptual understanding. Do we understand what's going on? There's this idea of strategic competence. Do we have a variety of different strategies? Do we know how those strategies work? There's this idea of adaptive reasoning. Can we take a real life situation, put it into math language, do our calculations, and then put it back in terms of that real life situation? And there's this notion of productive disposition. Do our students, do we see mathematics as something worthy to be something that we are capable of learning? And when I started broadening my view and thinking of mathematics as more than just answer getting, my students started to get more excited about math, and they started to want to learn math. And it's all about increasing student opportunities. Whatever I do, whatever any of us do, should really be increasing opportunities for our students. And I often wonder, is what I'm doing, is what the schools that I work with, are what we're doing really meeting the needs of every single one of our students? And we know that for many students, their needs have not been met. Many students have not found success in mathematics. But there are things that we can do differently to better meet the needs of our students. So in our time together here, I want to consider 3 different big questions. What content should be taught? What is the mathematics that's necessary for our students? The second question, what pedagogy? In other words, how should we be teaching mathematics? And then the third one that I'll just touch on at the end, what are some of the structures? What are some of the systems that we put in place? What do we need in order for our students to be successful? So let's jump in with that first question, the what content. What should we be teaching in mathematics? So during COVID, I saw this on Facebook. And it was evident to many mathematics teachers in the United States that our students had discovered this app called PhotoMath. Now, we knew that PhotoMath was around, but for whatever reason, during the pandemic, whether when it was first started, whether it was the year or so after the pandemic first started with COVID-19, we started to see weird solutions from students, non-ordinary ways of solving problems, things that we had not covered, things that they wouldn't learn how to do until several years later. And we knew that many students were now just taking a picture, letting the app do all the stuff, and then they were just copying it down. And I think that has implications for what we're teaching. This past spring, ChatGPT became a much bigger deal. And people started freaking out and realizing, oh no, there's this thing called ChatGPT, but it's more than just ChatGPT. There's all kinds of other artificial intelligence. And now our students can take a problem, put it into one of these artificial intelligence things for free, and it'll spit out an answer. This, I think, has implications for what we're teaching. If the only things that we are teaching are things that they can take a picture of and have an app find the answer, or if the only things that we're teaching are things that they can put into ChatGPT and get an answer, we're doing our students a disservice. We're not increasing their opportunities for success. We're not teaching them things that they need to know. They don't see a purpose then, because there's technology that will just find the answer to some of those problems. We need to think differently about what it is that we should be teaching our students. In many respects, we've had these conversations in mathematics education with calculators. 40 years ago, before calculators became much more reasonably priced, and before many students just automatically had a calculator, we had to wrestle with, what do we teach? Some of the computations weren't as important now that students have access to calculators. Some of the content that we currently teach just are not as relevant to students anymore now that we have ChatGPT, other artificial intelligence. So NCTM 10 years ago took a stance on, what do we think is the role of technology? And you see it here. Technology it absolutely must be used in our classrooms to help our students learn the ideas, to have our students make sense of the ideas, to help them to be able to communicate their thinking, to help them to be able to reason mathematically. Oftentimes, people say, all right, great, so you don't care about memorizing anymore. And I would argue memorizing is still important if we think about what it is that we want our students to have memorized. Is it really important for our students to have the formula of a cylinder memorized, or the formula for a triangular prism memorized? Or is it more important that they can do the calculations? They can take a real world problem, take a problem that has maybe part of a cylinder along with part of a rectangular prism, and figure out the composite volume. I mean, if we're being honest, our students can just say, hey Siri, what's the formula for a volume of a sphere? And they can find the answer. And I would argue, I want my students' mental efforts to be focused on making sense of things rather than just on memorizing. Another example, that quadratic formula is beautiful. I remember as a grade 11 student having to memorize that. We had to stand outside of our mathematics classroom. We couldn't enter until we could correctly recite the quadratic formula. And I wonder how many places we still demand that our students memorize that quadratic formula. But to me, it's much more important that they can use it correctly. It's much more important to me that they understand that the solutions that they find with that quadratic formula are the same thing as the zeros of the function, are the same thing as the x-intercepts if they graph it. I don't care necessarily if they have this memorized. It's more important that they know how to use it. They can interpret the answers, that they actually have it memorized. Again, I want to increase opportunities for students to be successful. And I think our overemphasis on having them memorize formulas is not increasing opportunities for our students to be successful. For many of our students, when we teach mathematics, when we've taught mathematics, when mathematics is taught by other people as memorization, our students don't see a need for it. And I want my students, I want all students, I want all human beings to have a recognition, an appreciation for mathematics, and to realize why mathematics is such an important topic. It shouldn't just be memorize, memorize, memorize. We need to get to understanding. We need to get to applications, applying our stuff. And I often wonder, what is more useful? I think, at least in the United States, we spend so much time on factoring trinomials. I love to factor trinomials. I'm good at factoring trinomials. I find it enjoyable. There's an importance to it. But in many places, we spend way too much time having our students work with factoring trinomials where they don't see a real-life application to it. They don't see a reason to do it. And when I'm thinking about the precious time that we have with our students, while this is a fascinating topic, Do I want my students to become overly proficient at factoring trinomials? Or do I want them to have a better sense about data and to be able to look at some statistics and to make sense? So I have a couple of examples of some data, some bad graphs. Here's a graph that definitely tells a story. When you look at that graph, it looks that whatever we're talking about here is decreasing. This is an actual graph that the state of Georgia, one of the southern states of the United States, used shortly after COVID-19 started. Somebody clearly wanted to give the impression that the rates were going down and COVID was not an issue. Those dates on the bottom that you can't read, they're not in order. It goes May to April, back to March to May. The dates are all out of order. When you reorder them and put them in correct numerical order, so you have April at the beginning, moving into May, rather than just all mixed together, this tells a drastically different story. I would much rather have students who can look at this and recognize there's something wrong with that graph than a student who can factor a whole series of trinomials. As another example, I saw this recently in a large newspaper, or a large online newspaper in the United States. Here, it's comparing the price of rent for an apartment compared to the household income. It tells a story. What it doesn't tell us is that those numbers aren't fully accurate. One of them has been adjusted for inflation. One of them has not been. And if we fully include the cost of living adjustments into there, it tells a drastically different story. I would much rather have students who can begin to look at graphs that are very misleading and have the presence to recognize what's wrong with that graph and to be able to then figure out what should it be. But at least in the United States, we spend so much time focusing on calculation. Can you factor this trinomial? Can you do this? Can you do this? And not as much with, hey, can we make sense of the data in the world around us? And we know that the world is becoming increasing. There's an increasing amount of data that is being used to make decisions. I want my students to be able to understand that. I want them to be able to draw their own conclusions. And I think the time is now, in light of the ever-increasing amount of data in the world, as well as the ever-increasing amount of technology that's available, it's time for us to take a close examination of the what have we taught. If we are still teaching the exact same things as we did 40 years ago, we are not providing the correct opportunities for our students to be successful. We need to take a good, hard look at what are we teaching and better meet the needs of our students. The second question that I want to address this afternoon is what pedagogy should be used. How should mathematics be taught? So from NCTM, we have a series of books called Catalyzing Change. In 2020, we released the Catalyzing Change in high school, followed shortly thereafter by the Catalyzing Change in middle school and the Catalyzing Change in early childhood. And in the Catalyzing Change series, there's 4 big recommendations. That first recommendation, as you see, is to broaden the purposes of learning mathematics. For most people, when you ask them why should we learn mathematics, for many they say it's to get a good job. That is one important purpose to learn math. But it's also important that our students, that humans, can use mathematics to make sense of the world in which they live. Think back to those data graphs. I want them to be able to make sense of that. I also want students who enjoy math, see the beauty in math. That second recommendation you see there is to create equitable structures. And we'll address that in a little bit, along with the recommendation for that developing that deep mathematical understanding. But that third recommendation is to implement equitable mathematics instruction. What am I doing to meet the needs of every single one of my students? Not just those who think that they are good at math. And all four of those recommendations really have connections between each other. All four of them are vital, and it's not like one of them is the key, is more important than the other three. All four of them are important, and all four of them interact with each other. But I really want to hone in on that recommendation number 3 for a little bit. The thinking about what should math instruction look like? How should we be teaching mathematics? This second idea here, it must be a collaborative endeavor. Students must be, as they're learning math, they must be talking with each other about the math. When they're talking about the math, they're developing a deeper understanding. They're starting to make sense of that mathematics. They're starting to get to that understanding point rather than just memorizing. Students must be able to solve problems in multiple ways. I want them to recognize, hey, here's one method, here's another method. I want my students to share their thinking, not just their correct answers. And correct answers are still important, but it's that thinking that goes with it. It's that reasoning. It's the sense making that is so absolutely important for our students. So 10 years ago, NCTM released Principles to Actions. And in this document, you see 8 effective mathematics teaching practices. I'm going to put these in a different arrangement. And I love this arrangement because it tells me 3 things. It's really saying the first thing that we do, we need to have a mathematical goal to focus our learning. I, as the teacher, I, as the instructor, I need to know what mathematics should my students be learning during this lesson. The second thing it's telling me is choose a problem wisely, choose a task wisely. Is this task going to be focused more on problem solving? Is it going to be focused more on procedural fluency? And it's usually a both, not one or the other. And then that bottom rectangle really says the same thing in 5 different ways. Those bottom 5 are really saying, they're telling me, I need to get my students talking about mathematics to develop a good, solid understanding of math. Math must be collaborative. Our students must be communicating with each other. Our students should not be just sitting and listening to the teacher talk and the students just trying to memorize what the teachers have said. They must be engaged in making sense of that mathematics. And I think in many places throughout the world, we were making some great strides, some great progress towards getting our students really focused on talking about mathematics. And then COVID-19 hit. And schools changed dramatically through the fault of nobody. Schools often shifted from that good conversation, from that good reasoning and thinking, to creating short little videos for students to watch at home. And then do 3 or 4 problems where they're just following a set of directions. And we know that that's not an effective way of teaching mathematics. But we did that because that's what we had to do in order to get through those first few years of COVID-19. And then in the United States, last fall, about a year ago, we started seeing headlines like this. It should surprise nobody that test scores declined. Our students missed so many days of school due to COVID-19. Our students were not engaged in their learning. They weren't thinking. They were just trying to memorize. And when I see this, it reminds me the way that we taught, the way that we were forced to teach through the fault of nobody, where we became math very much procedural. Here's step one, here's step two, here's step three, does not work for so many of our students. It does work for some. It probably works for many of us today. Many of us probably learned math by memorizing what the teacher told us. But that's why we're in mathematics education. That's why we're teachers. That's why we're professors. That's why we're other things supporting mathematics teaching and learning. But for so many of our students, just telling them step one, step two, step three is not effective. We have to look at what are we doing to get our students communicating with each other? What are we doing to have students make sense of the mathematics? So I want to think about this word struggle. And when you think of the word struggle, what words come to mind? And I'll pause again for a brief moment, give you a chance just to think, when you hear the word struggle, what comes to mind? For many people I know, when they hear struggle, they think like hard, difficult, frustration. Most people don't see struggle as good. And I want to argue this afternoon, struggle is necessary in order to learn mathematics. But I want to come back to that idea in just a moment. First, I want to think about learning to ride a bike. We know that there is struggle involved with learning to ride a bike. And yet we value that struggle. We recognize that struggle leads to something good. In fact, we value that struggle so much, we often give it some training wheels to help students begin to learn. The ultimate goal is not that the child rides the bike with training wheels. The ultimate goal is that that child rides that bike. I think the same is true for much of what we do in mathematics. If I think about using some hands-on things, and I'll share an example in a minute, I don't want my students doing the math with those hands-on things. I want them learning the math with those. I think about learning to swim. There's definitely a struggle involved with learning to swim. And yet we recognize that struggle is necessary to swim, to learn to swim. That swim instructor is not doing all of the work. It's not like the swim instructor has grabbed the child's arms and is propelling them, or grabbing the child's legs and kicking them. That swim instructor is saying, you know what to do. I'm here to support you. And I wonder, how often am I not like that swim instructor? How often in my class am I doing all of the work and my students are just sitting there? I want my students to be actively engaged. I want them to be making sense of the mathematics. I want them to be working with each other, to reason through, and to begin to understand rather than just memorize. So whether we're learning to drive, learning to ride a bike, learning a new song, learning a new instrument, learning a new language, we recognize that struggle is part of that learning. But unfortunately, in too many classrooms, we don't allow our students to wrestle and to think. We just tell them, here's step one, here's step two, here's step three, memorize it. No, they need to be actively engaged. They need to be thinking and learning. My job is to provide opportunities for my students to think, support them as they're engaging in those ideas, as they grapple, as they begin to mess around, as they begin to think. I want them to start to see connections between different mathematical ideas, different mathematical relationships. But I want to make sure I'm doing that for every single student. This idea of having my students reason, make sense, get to understanding is not just for some. Too often, our students who have been deemed, who have been decided, you're good at math, we allow them to reason, to make sense. And those that we see who are struggling, we don't allow them to make sense. No, every single one of our students must be allowed that opportunity to make sense of that mathematics. Every single one of our students must be able to understand what's going on and see the applications of math as they solve real world problems. So I want to share a couple of what would this look like in some classrooms. What are some ideas of how we might get our students to start to understand rather than just memorize? So what is this going to look like? So in just a moment, I'm going to give you a grade 2 mathematics problem. I want you to think about how would you find that answer. So how would you figure out the answer to 245 plus 98? Perhaps some of you think 245 plus 100 minus 2, and that's fantastic. Perhaps you think, let me take 2 from 245 and give it to 98, so I make it 243 plus 100, and then get the answer. Perhaps you think of it as 250 plus 100, subtract off 5, subtract off 2. Perhaps you did a traditional type of algorithm where you imagine that 98 is underneath the 245 and you add it by place value. Lots of different ways to solve that problem. And I often wonder, why is it okay for us as adults to think through this problem? And yet in so many classrooms, we do not allow our students to think through these problems. In too many classrooms, whether we're doing a problem like this or any other type of problem, too often our instructors say, do this, do this, do this. No, we have to give our students that opportunity to think, to begin to make sense of what's going on. I want to think about adding integers, adding positive and negative numbers. At least in the United States, this is an area that many students struggle with. Many students do not find initial success with that. Because in too many places in the United States, we teach it as rules. We just tell our students, here is what you need to do. They don't make any sense. They try to memorize it, and they start to memorize all kinds of rules incorrectly. So what could I do differently? Maybe I use some algebra tiles, or 2-color counters, or something else. I'm just going to show with a set of computer virtual ones, but I like to have my students use the actual physical ones. So when I look at a yellow piece, that's a positive one. A red piece is a negative one. So if I want my students to represent 5 plus negative 3, they can represent 5 plus negative 3 using those algebra tiles. And then they have to make a 0 pair. And there's going to be 3 different 0 pairs there. They get the answer of 2. But right now, we're really at that sort of that training wheel stage. Right now, they're just using these tiles to get the answer. They're not making sense. They're not learning that math. I want my students to learn the math, not just use the tool to get the correct answer. So then perhaps to help get my students to start to learn the big ideas, perhaps then I give them a set of problems. And I say, you use your tiles and you find the correct answers. I give them some more time. I do a quick little check and say, here are the answers you should have gotten. Right now, they're all smiling. They're confident. They're getting the right answer, but they haven't learned anything yet. All they've done is just gotten the right answers. So the second thing I'm going to have them do then is to start to make some drawings, because I want to get them to that point where they learn that mathematics. So I'm going to say, all right, let's draw a picture for -3 plus 7. And I tell them, no, we're not going to spend all this time sharpening yellow colored pencils, sharpening red colored pencils. Instead, let's just use minus signs for a negative, use a plus sign for a positive. And then I allow my students to choose how they want to show a zero pair. Some of them put an oval around it, some cross it off, some scribble it out, and they get the answer of 4. And then I give them a few more problems. And all of a sudden, I start hearing, oh, and I love that sound in a mathematics class. Because when I'm hearing that oh sound, I know they're starting to make sense. They're starting to figure out what to do. So I start out the lesson having them use those algebra tiles. Move the lesson so that we're doing some drawings of it. And then maybe I had them do a turn and talk with somebody right near them. Pose this problem 100 plus -101 and ask them to describe how they would find the answer. Students do not want to use all kinds of algebra tiles. That's too many algebra tiles to use. Students don't want to draw a picture for it. They want to just be able to figure out what is that answer. And because when they were making all those drawings, they were starting to make sense of that, my students make sense of that. They're turning, they're telling a neighbor, here's what you need to do. And then I have a student share out their reasoning. Usually their reasoning says, if the signs are different, or if I have one positive, one negative, subtract the number parts and choose the sign from the bigger number. I then put it into math language and say, oh, in math, we say subtract the absolute values, choose the sign of the bigger absolute value. Notice the problem that I give them, the actual calculation is not difficult. Notice I did not ask what's -63 plus 81. If I ask -63 plus 81, they may make a mistake with a calculation. There's not likely to be a mistake in the calculation with 100 plus -101. I want to see, have they understood what's going on? And then at the end, then we can provide some summary notes. We can provide more of those step-by-step at the end. But I think too often in mathematics education, we have started out with the notes. We have started out by telling our students, here is what you need to do, and then provide them some opportunities to think. Let's switch that. Let's instead provide them an opportunity to think and then give them some notes. Give them some tools to begin to reason, to begin to make sense, to begin to develop an understanding. And then we can provide some of those summary notes. We must give our students that first opportunity to begin to make sense. They need that first opportunity, not the only opportunity. We still, at the end of a lesson, to wrap it up, to summarize, we can provide some more of those step-by-step instructions, but we need to allow our students that opportunity to begin to make sense of it first. So let me try another example. If I give this student to many, or if I give this problem to many grade 7, grade 8, grade 9 students, for many of them, when they're 13 years old, 14 years old, 15 years old, many of them are going to use that distributive property. Many of them change the problem to 12x plus 8 equals 56, and then solve it from there. We know that there are other ways that they can solve that problem. They don't have to change it to 12x plus 8 equals 56 first. So I have an option. In my class, I could tell my students, hey, let me show you another way of solving that problem. For most of my students, if I just tell them I'm going to show you another way, for many students, they don't pay attention as I describe that. But instead, I could switch my problem and make it like this. And say, Camden says here's a different way that you could do that problem. And then ask the students, does Camden's way work? And all of a sudden, we have moved from me just telling them, here's another way, where many of them aren't really listening, to getting them actively engaged, thinking about, does this way work? Does it not work? But I had to be careful. If I only do a problem like this, when the answer is yes, my students start to realize every time he asks, you say yes. So I have to make sure I choose some no's in there as well. So here's an example of one that the answer would end up being no. Figure out what is that common error, that common incorrect solution that students are going to have, and put it in, have the class make sense of that. As a class, decide, is this appropriate? Is this not appropriate? I think about learning the vertex form. For me, I just memorized. I was just told a quadratic relationship can be written as y equals a times x minus h squared plus k. The vertex then is at hk. A affects the direction and the width of that opening, if it's stretched or if it's compressed. For students, they don't really care. They're not motivated to try to find patterns in there. So what about if instead I use a graphing calculator? Or what if instead I use a free online tool called Desmos? And I have a short little video. There is no sound to this video. I'll talk through what I do with that. So what if I go to there and say, all right, hey class, you graph y equals x squared, and allow them some different numbers to choose. They see that changing that number in the inside is changing it left, right. Or I could then go and put some sliders on there and have the computer automatically start moving that h value, automatically start moving that k value, have that computer automatically change that a value. And all of a sudden, my students are making sense of that. They're recognizing, oh, that h is moving it left, right. That k is moving it up, down. The a is affecting the direction of the opening. And yes, I usually do end up having all three of them moving at one time, as I showed there, so that my students can begin to appreciate that. I would argue something like this, or using a graphing calculator, is much more effective. It's much more motivating for our students than just telling them, here is what you need to do. This is how mathematics should be taught, not just here's step 1, here's step 2, here's step 3. When I think about properties of exponents, I think there's a lot of work that we can do with that as well. Instead of me just telling them all of those different rules, what about if instead I say, oops, what about if instead I have them put it out in expanded form? What if I tell them, hey, you find the rules? And when they find the rules, they begin to make sense of that. They start to see the shortcuts. They find those algorithms. And when they discover those algorithms, it sticks with them a lot longer. They've made sense of what's going on with that. That next moment, I can switch it then and say, hey, what if I add x to the second to the third? What does that really mean? Have them find that pattern. Have them start to realize x to the second, x to the third. Oh, that's 2x's, 3x's. That gives me 5x's total. X to the second to the third. That means I have 6x's total. Now, all of a sudden, I don't have students who are just memorizing. I don't have students who are guessing at which one is the adding, which one is the multiplying. They can think, they can reason, they can make sense of that mathematics. I can do the same thing with those properties of the zero property. And we know that so many students want to think that 4 to the 0 is really 0 rather than 1. And they think that it's a stupid rule because they don't understand why. Let's share that why with them. Let's explain. Let's have them make sense that 4 to the third is 64. If I subtract 1 and make it 4 to the second, I have to divide by 4. So 64 divided by 4 gives us 16. Subtract 1 again. I'm at 4 to the first. Divide by 4. Subtract 1, divide by 4. And all of a sudden, students realize that's why something to the 0 power is 1. It makes sense to them. We need to continue to have math as making sense, not just as rule memorizing. Maybe when we're introducing functions, maybe we use an online thing. And this is a free one from a great online website called Desmos. And one of my favorite activities is Function Carnival. And I wanted to share just briefly, what does it do? Again, there's no sound. I'm just going to talk briefly through it. So it begins by having the students, press play. They can see a man jumping out of or being shot out of a cannon and then come back down. They can be asked to describe what's going on. On that next screen then, they're challenged to draw a graph. So maybe a student thinks that's what the graph is going to look. They can press the play button and notice they see the person, the real person, as well as the person that they have drawn. Provide an opportunity for them to change their thinking. Maybe the student recognizes, oh, it needs to be not quite a straight of a line, a little bit more of a curve initially. They can start to make sense. They can start to see all of those different relationships. From the teacher end, you can see all the students' work, and invariably a student's going to have a goofy thing like this. Share that student and let them see, let the whole class see, oh, here's what that graph would look like. And when I think about what's more engaging, me just telling them or providing them the technology tools to actually work through a problem like this and to begin to make sense. Let them start to draw those graphs and have the technology come up with what would it look like right off the bat. I want my students to be motivated to learn math. I want them to recognize that they can do math. And with things like this, they start to see, they start to believe that they are capable of learning mathematics. But I also recognize getting my students to share their thinking is a difficult concept for many students. Many students are nervous to share their thinking because there is this idea that they might be wrong. So I like to do things to have my students just get used to talking in math about math. So one of them that I've started doing over the last few years is problems like this. In just a moment, I'm going to show you a dot figure. I want you to figure out how many dots do you see and how do you see it. So I'll display it for about 3 seconds. All right, so how many dots did you see? Hopefully, you all saw 7 dots. But I'm going to guess that we saw those 7 dots differently. I'm going to guess that some of you perhaps saw it as a row of 2, a row of 3, another row of 2. Perhaps some of you thought about it in terms of a dice, and you saw that middle 5 plus 1 on each of those 2 ends, you still get 7. Perhaps some of you saw it as 1, 2, 1, 2, 1. Perhaps some of you saw it as a group of 3, another group of 3, a group of 1. But no matter how you saw it, we get that same answer of 7. When I do a problem like this with my students, they're willing to share their thinking. They want to share their ideas because they know there's lots of different ways that we can get that same answer. The same thing needs to be true when we're thinking about a mathematical problem. We need to recognize, we need to help our students recognize there's more than one way that we can get to that answer, and yet that answer is still going to be that same thing. And I wondered over the summer when I got ready to share this idea with a group of teachers, if somebody had already created a website that has all of these, and lo and behold, somebody has already created a website. I just did a search on math.talks, and somebody has a whole list of all different ones there. Another one that I'd like to use is an idea called which one doesn't belong. This was the original name for it. Some people are now starting to change it to which one is unique. And I like to ask my students, which one of those 4 is unique? My students often jump to 9 is unique because it's the only single-digit number. 16 is unique. It's the only even number. 43 is unique. It's the only one that's not a perfect square. It's the only one that's a prime number. Some of my students said 9 is unique because the digits don't add up to 7. 1 plus 6 is 7. 4 plus 3 is 7. 2 plus 5 is 7. This is not 7. That was a surprise to me that students saw that. 25 is usually the most difficult one for students to come up with an idea of what makes that unique, other than saying it's the only one in the 20s. And that does make it unique, but I tell them that's a little boring. My favorite answer, I had a student one time that said 25 is the one that's unique because you can't color in anything. In the 9, you can color in the circle part. In the 16, you can color in the little circle part. With 43, you can color in the triangle. Nothing to color in on the 25. That makes that one a unique one. I was surprised by that. But just as with the dots, this provides an opportunity for students to begin to share their mathematical thinking. And this really ties into, I want my students to develop a positive mathematical identity. I want them to recognize that they are able to participate, they are able to learn mathematics. And why is this so important? In this wonderful resource, the authors share 5 different ways that we can teach mathematics to every single student. And one of those 5 ways you'll notice is affirming those mathematics learners' identities. There was also a group of researchers 6 years ago that looked at a bunch of mathematics education research and said, here are 9 practices that we should be doing to better meet the needs of our students. And one of those is that positioning students as capable. It's important. I need to think about what am I doing to help my students best learn mathematics. One of the things that I like to do with my 14-year-old students is have them draw an emoji. I want to start to begin to see how do they view themselves in mathematics. And let me just briefly share a couple of my favorites. Here is probably my all-time favorite. Here is a student when they are struggling, they start sweating, and they develop bad breath. But I want to close with thinking about that third big question. So I started thinking about what content, what should we be teaching our students? Then we started to think about how should we teach it? And now I want to just touch on what are some of those structures that we need to have in place? What are some of the things that we do in schools that prevent students from best learning? And what can we do to better meet the needs of students? Thinking back to those 4 recommendations from catalyzing change. And that second recommendation is those equitable structures. And in the United States, in too many spots, we group our students based on how we think based on their perceived ability. And we know that it allows some to have access to mathematics where others do not have access to mathematics. And in the United States, that is a structure that we need to continually break down. We need to have mathematics available for every single one of our students. In many of our current states, in many of our schools, they're beginning to consider what should high school mathematics look like? What should grade 9, grade 10, grade 11, grade 12, what should it look like? And I want to just wrap up our time sharing 3 different stories, 3 different states that are thinking of differently about what are the structures that should be in math. Many states are recognizing we need to have 4 years of high school mathematics. And for those first 2 or 3 years, our students should all be in that same pathway. It's in that 3rd or in that 4th year that maybe we have different pathways. And those pathways have to be based on student interest. What does a student think that they're going to do for a career? If they're going to do something in the humanities, the performing arts, the fine arts, maybe a class in quantitative reasoning is going to be best for them. If they think they're going to do a social science, nursing, psychology, other such things, maybe a class in data science or a class in statistics will be more beneficial. If they're going to go into the sciences, into mathematics, into engineering, then perhaps a calculus class is best for them. But students need to have some sense, and most students have some sense at that point in time, what careers they might be interested in. So three quick states. One of them is in Ohio. Right now, Ohio, in the Midwestern portion of the United States, all of their 9th graders take either Algebra 1 or Math 1. Their 10th graders take Geometry or Math 2. And then for their final 2 years, depending on what their career interest is, they take a variety of different math classes. Maybe they take Algebra 2 if they're interested in those careers. They take statistics or they take a data science. It's based on their interest. Oregon, in the far northwest of the United States, they have a little bit different structure. Their freshmen, their 9th graders take a class in algebra. Instead of taking a full year of geometry, they do a half year of geometry, a half year of data science. And then in those last 2 years, they take a different path. Are they more interested in the calculus pathway, that data science pathway, that quantitative pathway? In Georgia, they have a different structure with theirs, and they have several different spots. One of the things that I so appreciate about Georgia is when they have those opportunities for a student to accelerate a little bit and to move ahead, the 10th grade students are taking that same class then as that 9th grade. It's not 2 separate things, it's that same one, and it's providing different types of opportunities. So my challenge to all of us, as we think about increasing opportunities for students, what content, what should we be teaching to better increase opportunities? What pedagogy? How should we be teaching mathematics to better meet the needs of our students? What structures do we need to put in place in order to better meet the needs of our students? So I want to conclude by just saying thank you. Thank you for joining me this afternoon as we think about how do we increase opportunities for all of our students. If you would like a copy of the PowerPoint slides, you may gladly email me. I am happy to share those slides with you. Or if you have questions later on, I am happy to address those questions. So thank you very much for your time. And thank you for this invitation to join this group and to share some ideas.
Thank you very much, Professor Dykema. We normally do have about 15 minutes for questions. Is that all right with you?
That is fine.
All right, thank you. And so I will kick it off and pido a las personas que no quieren hablar inglés que escriben sus preguntas en el chat y los miraremos. I would like to kick it off with your discussion of content, the first part of your talk. And you consistently used the words rather than. And for example, one of your examples was, instead of factoring, make use of, or versus making use of data, rather than. And I'd like you to explain a little bit what you mean by rather than.
Yeah, I think it can be both. One of the things that we often do to our K-12 schools, to our schools, is just continually add more things in and say, you have to do this and do this and do this. And I want us to consider, what are those things? Factoring trinomials, for example, is important. But in many spots in the United States, we spend 6 weeks on factoring trinomials. Is 6 weeks really an important 6 weeks to do with that? Or could we spend 3 weeks on factoring trinomials and then give 3 weeks to do something else, maybe with some of those data and that reasoning? So there are some of those math skills that I think that historically, traditionally, we have spent so much time doing that technology often can replace, and we can de-emphasize some of those, spend less time on some of those concepts to allow us more time for on things that may better meet the needs of our students.
Okay, so you're saying adjusting time, not necessarily
Not necessarily
eliminating
getting
one
rid of,
thing.
no. But I mean, there are some things that we can probably get rid of that aren't necessary, but there are still many of those things that it's really more of a time adjustment as opposed to totally eliminating a topic.
Okay. Thank you. Go joins us from Brazil. Yuriko, your question.
The microphone, Yuriko.
We don't have your audio, Yuriko.
Yes, now I am open. Thank you very much, Dr. Kevin. A very interesting talk. And one slide that you showed about the lowering of the scores after the COVID-19. This is a worldwide phenomenon. We are everybody dealing with it.
Yes.
So the nature of our mathematics classrooms is very, very important to discuss. So how the American schools are dealing with this lowering to catch up the curriculum flow and the curriculum reform. And so thank you very much.
Yeah, and it is a very difficult thing. It is a thing that American schools are still attempting to try to come up with good ways of doing that. And for many of them, we need to recognize, if I have a grade 6 student who may be missing some things from grade 3 or grade 4, I have to find ways of incorporating those within my grade 6. I can't stop teaching grade 6 and go back and try to reteach grade 3,
Sure.
reteach grade 4, because the students don't see a need for some of that, and then they start to feel even worse. So we're trying as much as we can to teach the content that they should be learning, and then try to fill in some of those pieces. It's a difficult thing. And I would argue, I know that when we continue to teach math as getting to understand what's going on, to make sense, rather than just memorize, then all of a sudden they start to see a reason for it. And some of those gaps that may have been created during COVID start to eliminate, because they start to feel more confident with it. But without a doubt, mathematics education worldwide is wrestling with, is trying to figure out how do we help our students meet their needs, and how do we get some of those test scores back up?
Thank you very much. Just one question, very small question. Is the technology supporting this catching up in American schools, even for socioeconomical vulnerable people?
Yeah, that's a great question. So I would say because of COVID-19 and during the pandemic, there was a lot of government money that was spent on schools for schools to provide technology for students. So many of our students, even those students who live in communities that are very impoverished, many of them have devices now from the school, and they're able to utilize those devices to help them learn some of that mathematics and to begin to make sense of that. So we are very lucky that way.
Yeah. Thank you very much. I will leave time for other questions. So thank you very much.
You're very welcome.
And still, I would like to ask a second question. Also, at the very beginning of your talk, you spoke about, instead of memorizing the quadratic formula, teach students how to use the quadratic formula. And I would just like to ask you about showing the reasoning behind the quadratic formula, why it works, and how it was first discovered so many years ago. Just the difference between how to use and knowing why it works. What would you say to my question?
And I think that's wonderful if you show them how it was created. But I think in too many high schools in the United States, we just tell our students, memorize this. We don't give them any reason where it came from. We just expect they're just going to memorize, and our students think this is just some formula that just somebody happened to discover one day and it works. I think it's much more important to, as you say, either share, hey, here's how somebody created this, so they see a purpose for it. And then we can just provide that and say, all right, now that you know how it was created, now you know where it comes from, now let's use it. But too often, I think we skip over that, how was it created, and just jump right to, let me provide this formula for you and just tell you what to do with it. No, they need to understand where it came from, what it's really telling us to do. So I think it's wonderful when teachers do spend that time and show how it was derived and how somebody discovered it at one point in time.
Rafael, I would ask you to look at the question in the chat and translate it. Meanwhile, Nicolas may ask his question. Okay. Nicolas.
Well, there is a question in the chat in which we say that how much the opportunity has to be centered in the mathematical activity for the teaching or for the learning of the student. I mean, I don't know if I'm translating well, because I don't understand well the question.
Yes, I was wondering about translating centradas, and that's why I asked you to translate it.
Yeah, because centradas. No, I don't know how to translate centradas.
The focus of activities.
So,
central focus of activities.
Central focus of activity. Yeah. But how?
For the learning of students. What could be the focus? Central focus.
Yeah, that could be a good translation.
The opportunities of math activities for learning students. Yes. So, what should be the focus?
The focus.
The opportunities of mathematical activities for the learning of students.
Yeah. So I think teachers need to know going in, what is the math idea that I want my students to learn? And then find an activity, create an activity, do something to help them develop the understanding of that idea. For example, when I looked at the adding integers, my goal, my purpose for that activity was that they would learn how to add positive and negatives. and then you structure an activity to get them to that point. When I think about the exponents, my purpose may have been for them to learn that 3 to the 0 power is 1. And then I structure an activity to get them to that point. When I see a
Okay.
great question
Thank
in the
you.
chat, yeah, I see a good question in the chat box as well. And
Yes,
that is definitely a challenge for our teacher training. And most teachers in their teacher preparation, in their teacher training, are trained to do it that way. And then when they go into schools, too often it goes back to the way that we've done it for however many years, because it's more difficult to get students to understand what's going on. It's more difficult to find resources, to find lessons that have already been created for it. It's much easier just to go back to here's step 1, here's step 2, here's step 3. So that is definitely a huge challenge in the US. Our teacher training educators are doing a great job of telling teachers what they should be doing. It's the getting it to be fully implemented. And we're starting to get better with that. And change is slow, change is difficult.
Nicolas, your question.
Yes, thank you, Professor, for your fantastic presentation from both the descriptive and normative perspectives. So I would like to ask you a question about both of them. From the descriptive perspective, where can we find information about the curricula and what they are doing in the US? And from the normative perspective, what do you think are the most important things a program should have to be appropriate using the available technologies? Thank you.
Very good questions. So for the curriculum, most of when I think about what standards, what's the actual material that teachers are teaching, most states are still using the Common Core state standards. It was a nationwide effort to have all students learning the same material. Many states are now creating their own sets of state standards, but most of them are still based off of that Common Core set of standards. So that's a good spot to look for what are the big ideas that are being taught. When I think about technology, what are the big important things for the technology? I think when the technology, I want it to be something where if I know what is my math goal, if I know what I want my students to learn, I want that technology to be supporting that. I want my technology to be something that's going to help my students develop that understanding of the material. I don't want the technology, I want it to be to enhance it, to get them excited. I don't need a technology that's boring for the students. I don't need my technology to be only just practice problem after practice problem after practice problem. I want that technology to help engage my students. And when I think about that man being shot out of the cannon with the parachute, that's engaging my students. If I get them technology where they have to do a whole bunch of problems and then a little bubble pops up and says, nice job, that's not engaging for my students. And I think there are, at least in the United States, sometimes some of our technology companies, all they've done is taken a worksheet and turned it and put it into a computer thing. That's not helpful for students. I want that technology to be something where they're learning that math, where they're engaged, where they're able to begin to make sense of what they should be learning.
Thank you very much.
Thank you. Do we have any more questions?
No.
Well,
Well, there is a question written in English in the chat.
he has already addressed that question.
Yes.
Yeah, I think I answered Sylvia's question.
Yes.
Yes, he already addressed that question. Yes. If not, thank you very much again, Dr. Dykema, for joining us this afternoon.
Thank you.
We really appreciate it. I'm sure that you can see the names of many of the people who have been here this afternoon. I would like to make it clear that these are people from many different Latin American countries who are attending your talk this afternoon. Thank you once again.
Wonderful. Thank you. Have a good day.
Thank you very much.
Y-
Very interesting lecture.
Thank you.
Yes, right. I agree, Eurico. Osvaldo, can you tell us what we have for next week?
Ok, de acuerdo.
¿Qué es lo que tenemos para la semana que viene?
Para la semana que viene tenemos en nuestro seminario la conferencia de la doctora Diana Isabel Quintero Suica, egresada de nuestro programa de doctorado en educación matemática, y nos hablará sobre el aprendizaje de la educación en estadística en secundaria, la búsqueda de un modelo de razonamiento repetitivo.
Ok, muchas gracias. Gracias a todos por asistir. Nos vemos la semana que viene. Muchas gracias. Hasta luego.
Gracias, hasta luego. Hasta luego,
Chao.
doctor Yurico, muchas gracias, y a los demás.